And once you, okay, now you can take it away.
Okay, thanks very much for the invitation to come and talk. So far, it's been a really interesting meeting, although it's been a little bit early for me since I'm up here in Alaska, so it's about 6:30. So I apologize if I'm a little bit slow because I had to get up pretty early. Okay, so what I wanted to talk about today was just give a little bit of an overview so this was sort of the assigned topic I had, so talk about nuclear equations of state. And I'm sort of going to focus on underlying physics and motivating a little bit why the nuclear equation of state's important for this problem, and also look at a use case of looking at the sensitivity of a slightly different problem in nuclear equation of state that we've recently done. So looking at the sensitivity of the core collapse supernova explosion mechanism to the nuclear equation of state as sort of maybe an example case of what could be done by systematically varying the properties of the nuclear equation of state, potentially in neutron star mergers. Okay, so and I'm Luke Roberts. I'm a assistant professor at the National Superconducting Cyclotron Laboratory at MSU. And so I'm normally in Michigan, but since we're all stuck at home, I decided to come up to Alaska. Okay, so just as one, so I think that there have been a number of clear motivations for why the nuclear equation of state is an interesting problem for neutron star mergers in terms of what the in-spiral gravitational wave signal is going to look like and those sorts of things. But one example is its impact on nucleosynthesis in material that's ejected from the leftover accretion disk. So this is some work that we did a few years ago. So the idea here, right, is after the merger, you're left with an accretion disk around a hypermassive neutron star that might live for some period of time. Okay, and while that hypermassive neutron star exists, it's going to be emitting a copious number of neutrinos. Those neutrinos are going to interact with the accretion disk that's surrounding it, and they're going to change the electron fraction of that material. And it's also going to provide a different boundary condition for the accretion disk. Okay, and so if we look at that, that's going to end up changing what the distribution of the electron fraction in this material is. So I hope, can you see my mouse? I think you can. So you can see that, as you go from a hypermassive neutron star for H000 that doesn't live for any period of time, you get an electron fraction that only goes up to maybe 0.2, peaks around 0.25 at most. But then as you go to a longer and longer lived hypermassive remnant, longer and longer lived hypermassive neutron star, you get a higher YE and a broader range of YE. Okay, and obviously the lifetime of the hypermassive remnant is going to depend on the parameters of the binary, but it's also going to depend on the nuclear equation of state. Okay, and this is of course important for the eventual R-process nucleosynthesis that might happen in these outflows. So here's just a calculation. This is a chart of the nuclides with the number of neutrons on this axis, number of protons on this axis, and this is just looking at some neutron-rich material that might have been ejected from the disk and following the nucleosynthesis that goes on here. So this is calculation done with Skynet, so I also do a lot of nucleosynthesis stuff, so if people are interested in nucleosynthesis-related collaboration, I'm always interested to talk about that. But so what's happening here, right, is we're starting out with a bunch of neutrons down here, a bunch of nuclei in NSE, and then capturing neutrons up to higher and higher masses. Okay, and I think most people, and this is of course exactly the YE distribution you get, determines how neutron-rich your material is. Okay, and so I think most people are aware of this, but this has quite a large, so the YE has quite a large impact on, the electron fraction has quite a large impact on what nuclei are eventually synthesized, and thereby also what the kilonova light curve that might be associated with such a merger is going to look like. So here, I'm just showing some calculations of nucleosynthesis as a function of the electron fraction in this material along the x-axis here. And the main line I want you to look at is this thick black line. So this is the abundance of lanthanides and actinides in this material as a function of YE. And you can see that right around 0.25 YE, this shoots way up. Okay, so it goes from basically no lanthanides and actinides are being produced So you're only producing material up to the second R process peak, but not beyond it. But then as you go below that YE, you become electron fraction, you become more neutron rich. You start producing these lanthanides and actinides, which, as well known, provide a large opacity for the ejecta, okay, and make the optical transient associated with the ejecta redder and longer lived. Okay, so that there's direct observational consequences of this. And so then that gets maybe imprinted on the ejecta from the disk. Okay, so if we have a longer lived hypermassive neutron star, so if we have an equation of state maybe that supports more massive neutron stars, then we might end up with a larger YE, or a distribution of electron fractions in the ejecta that has higher YE, okay? And then we might either be more or less biased towards the first R process peak, and that may have some impact on whether or not we end up with a blue or red kilonova that's associated with this merger. Okay, so that's just one case where we have where there's some motive where we can motivate why we'd be interested in the nuclear equation of state. And so what I want to talk about for a lot of the rest of the talk is just sort of the basics of what go into finite temperature, arbitrary composition, inhomogeneous astrophysical equation of state, right? So to model, so all these systems in the fluid, right, there are a number of different components that we maybe need to consider. Of course, we're going to have arbitrarily relativistic and degenerate electron and positron gas. Okay, so that component is fairly straightforward to deal with, right? As long we're basically assuming that those electrons and positrons are non-interacting. So we just need to do some Fermi-Dirac integrals and we can get those results. There are also photons that are generally trapped in the fluid, and those can provide a substantial reservoir of pressure and energy at various times, and those also need to be included in the equation of state. But once again, they're even simpler than including the electrons and positrons. The complexity comes in when we want to deal with nucleons. So first of all, we have to deal with high density regions. So at and maybe a little bit below nuclear saturation density, we have homogeneous interacting nuclear matter. So we have nucleons that are basically forming a liquid, and that's going to sort of nuclear saturation density and a few times nuclear saturation density. But the other thing that we have to deal with, at least at lower temperatures, is that there might be some sort of liquid gas phase transition for nuclear matter. Okay, and then material is going to become inhomogeneous, and we're going to have things like pasta and nuclei form. Okay, and so those things change the thermodynamic properties of the medium, and they also change the transport properties of the medium. So we just heard from Josh talking about neutrino transporters, transport in general. Okay, and the neutrino opacities that go into the right-hand side of those transport equations are going to depend on exactly, okay, what the constituents of matter are at these low densities. And then we have to also worry about things like Coulomb interactions and those corrections to the equation of state. Okay, so the things on the left side of this column are sort of things that you definitely, almost all equations of state are going to deal with in some way. The things on the right-hand side are other things that might show up in the equation of state and could play a very important role in the eventual evolution. So we could also have muons show up, okay, and so those muons can hold some charge and change what the electron and positron contribution is, and thereby change the equation of state at some densities. That's maybe less, well, no, those are likely to be potentially present in parts of the remnants of the neutron star merger. The other thing that's potentially interesting, and I won't talk about it too much today, is the possible presence of new phases at high density. Okay, so maybe there's a phase transition to quark matter or something along those lines. And so as you go to a more massive neutron star, you get a larger and larger region that has this quark matter, and maybe you undergo a first order phase transition that can change things. Or you could maybe go through a smoother sort of semi-phase transition and start to produce things like hyperons that also would soften the equation of state relative to just a pure nucleonic equation of state. Okay, so there are a lot of different things that can go in here, but modeling, so I just want to talk about a few different ways that especially this part of the equation of state is modeled. Okay, so just visually, we have to go through sort of all three of these regimes if we want to have a tabular nuclear equation of state that we can use across the wide range of densities that might go from 10 to the 16 grams per cc down to 1 gram per cc, and from temperatures down to, well, I said T approximately low, which is not very useful, but maybe down to 1/100th of an MeV, going all the way up to 100 MeV, which you might encounter in some regions of the remnants of a merger. Okay, and so you need to be able to go from this homogeneous interacting nuclear equation of state to this inhomogeneous equilibrium equation of state, where you deal with this either through nuclear statistical equilibrium or some sort of liquid droplet model. And then eventually, maybe you need to make this transition from equilibrium to a non-equilibrium EOS, where you're tracking all the nuclear species, like we're doing in the Skynet calculations, or those nuclear reaction network calculations that I showed earlier. And so following the entire composition of the medium when nuclei fall out of equilibrium. Okay, so I want to talk about now, I want to think about, first, let's think about how maybe we model this homogeneous interacting nuclear equation of state. Okay, and so for the models that I'll probably talk about most here, the way we model the bulk matter equation of state, or the homogeneous matter equation of state, is through the Skirm model. Okay, so the Skirm model is a zero range effective interaction. So it's a phenomenological model for the interactions between nucleons. It also could just be thought of as an energy density functional theory. But essentially, it's just some sort of generic interaction, two-particle interaction that has a number of terms, and it has a number of basically parameters that go into that interaction. So there's T0, T1, T2, T3, X0, X1, X2, X3. Okay, and so those parameters essentially are generally fit to properties of measured properties of nuclei, things of that nature, to produce a particular Skirm interaction. Okay, but you can also take that Skirm interaction in the mean field limit, or think of it as an energy density functional, and you can write down what the energy density should be for homogeneous interacting nuclear matter. Okay, so you get some, well, you get some kinetic contribution from these two terms here. Okay, we'll talk about those in a second. But then you get some density dependent potential contribution to this energy density. Okay, and that ends up depending on, well, what's the density of the medium? Y here is the electron fraction. So what's the symmetry, or how asymmetric is that matter? Okay, so you get a very different energy per particle for pure neutron matter, which would be when Y is equal to 0. So you get always increasing, versus nuclear matter, where you have an energy as a function of density here. So this is density and number of baryons per femtometer cubed. Okay, and there for nuclear matter, well, you get some minimum in the energy you find, which is obviously around where you get nuclear saturation density. Okay, so but the interaction contribution of this energy comes in here. Okay, and then you also just have this kinetic contribution that's just a couple of Fermi integrals, and this looks almost exactly like the ideal gas equation of state that you would normally see. Okay, except for that you replace the mass, the bare mass, with some effective mass that takes into account the fact that the potential energies of the nucleons might have some momentum dependence. And you see here that these parameters A and B, and those can be directly related to the underlying parameters of the Skirm interaction. The other thing that they can be directly related to is, since there's a finite number of parameters, you can map those directly to the observable properties of nuclear matter. So if you choose a set of parameters, you would find a particular value for this minimum of the energy at the nuclear saturation density. So that would fix the nuclear saturation density. You also have a binding energy per nucleon here at at saturation. So that would predict that would predict a binding energy, predicts an effective mass. So there's some ways that you can get at measuring this effective mass, which has maybe has the largest impact on the temperature dependence of the equation of state. You can get the compressibility, the symmetry energy, or you could tie this to things like the maximum mass on the radius of a 1.4 solar mass neutron star. Okay, so but that's just the bulk matter equation of state. But the problem with just taking the sort of mean field mean field model using the Skirm interaction is that there ends up being, at least for close to symmetric matter, where you have equal numbers of neutrons and protons, there ends up being a liquid gas phase transition that occurs. And this liquid gas phase transition essentially is sort of the beginning of the formation of nuclei. But the basic point is that if you look at the pressure as a function of density for one of these mean field Skirm interactions, is that for a YE of around 0.5 or 0.4, even 0.4, right, there's a region that's thermodynamically unstable. So the pressure is going down with density, and that's going to be unstable to some sort of spinodal instability, right? Or you could think about this as the free energy. So to be stable, you would have to have the free energy of a single phase be less than the free energy of two different phases where you split into two phases that have different densities, okay? But if this is not the case, so if you can find two regions where if you split into those different densities at fixed temperature and you actually had a lower free energy than the homogeneous matter, then your system is going to undergo this phase transition and split. Okay, and so there are a number of ways to deal with this. The simplest approach, and one that you're sort of guaranteed to get thermodynamic stability, is to use either a Maxwell construction or a Gibbs construction. Okay, so if I take my free energy of this material and I sort of say, okay, I can have volume 1 of density 1 and volume 2 of density and YE2, okay, and minimize this subject to the constraints that I have some total volume. Z here is the charge in volume 1, is the number of protons in volume 1, N is the number of neutrons in volume 1, and similarly for volume 2. And so if I say I have to have some total volume, some total number of protons, and some total number of neutrons, minimize this free energy subject to constraints, you get sort of this standard Gibbs construction, where in both of the phases I have to have chemical potential equalities, and I also have to have the same pressures as well as the same temperatures across this phase. Okay, and so you can build a very simple equation of state like this that has the thermodynamically stable and works across the whole temperature density YE space. And we have that available, and it's actually maybe a nice way to be able to put in to systematically vary the Skirm equation of state and build equations of state that will work across the whole thermodynamic parameter space. Okay, I'm going a little bit slower than I thought I would, so I'm going to skip this. This is just a way to visualize the phase coexistence boundaries that show up. So you end up with regions in neutron density and proton density for a fixed temperature, where you have this region where you know that you're going to split into two phases, okay? And you're going to end up, if you're sitting here, you're going to end up with some fraction of the material in your system at this density and some fraction of the material in your system at this density. Okay, and this is just maybe a little bit clearer description of the regions where you expect to have this mixed phase if you're just doing this Gibbs construction. So here's around nuclear saturation density, and you have this region at low temperature where you have these two phases, but then as for any particular YE, there's a critical temperature above which there's no phase transition. So at very neutron-rich material down here, that critical temperature is maybe only 4 or 5 MeV, but as you go up to symmetric matter, the critical temperature for having inhomogeneous material is somewhere around 18 MeV. So you're certainly going to go through some of these regions. Okay, so this is sort of this Gibbs construction is the simplest way to deal with this. A somewhat better way to, more realistic way to deal with this, if you're interested in the transport properties, would be actually to map it onto a nuclear statistical equilibrium equation of state. So that's where you assume that you have a large distribution of nuclei, but the chemical potentials of any of those nuclei are just equal to the chemical potentials of the number of neutrons in that nucleus times the number of the neutron chemical potential plus the number of protons in that nucleus times the proton chemical potential. But to do this, especially for very neutron-rich conditions, you need a large ensemble of nuclei to be able to get to the very to realistically treat the very neutron-rich conditions that you're going to encounter. So if you think about this on the NZ plane, you're going to end up with nuclei that are very far out here, so very far away from stability. And so you have to have some way, you have to have some model for those, because most of their properties haven't been measured in the laboratory. Okay, an NSE equation of state like this is actually going to be appropriate for most of the accretion disks. So this is going to be fine for densities up to maybe 10 to the 12 grams per cc. And this naturally takes into account things like the energy released from the formation of nuclei, and so it can get a lot of the energetics right if you're just trying to understand the properties of the accretion disk. But if you just use sort of a nuclear statistical equilibrium equation of state that doesn't have any corrections to it, it does have some problems. So here you would still predict, if you just used treated nuclei as point particles, nuclei would actually persist past saturation density, because the nuclei in the simplest NSE picture have no knowledge of nuclear interactions except through their binding energies and their internal partition functions. Okay, and then you would get a high density behavior would be unreasonable, and you wouldn't really get this liquid gas phase transition occurring where you know it should happen. So one way that people deal with this, and sort of the main equation of state that's on the market right now that does this, is this Hempel EOS. Okay, and they use more or less nuclear statistical equilibrium, but they assume that all the nuclei have finite size. So they have a finite volume, and that keeps nucleons out of the volume of the nuclei, and essentially pushes the nucleons to higher density if nuclei exists. And so that naturally makes nuclei disappear as you go through this, as you get to near saturation density. Okay. The other model, and this is the one that we have an open source framework for building equations of state using this, is the Latour-Swesty, essentially two-phase model. So this is sort of an extension of this Gibbs model that I was talking about before. So it's essentially allows for two phases, but then includes corrections for the fact that there must be some surface between the two different phases, and there's going to be some energy associated with that surface because there's going to be some surface tension. It also takes into account Coulomb effects and the kinetic energy of these basically bubbles of high density phase that are floating around low density phase. So if you look at what the free energy should look like in this case, it has the same form as you would have for the Gibbs construction, but then you have some other contributions to the free energy that come from some surface contribution, some Coulomb contribution, and some translational contribution. Okay, and if you minimize the free energy, you get a set of equations that look very similar to the Gibbs construction, except now that you get some correction terms, these B terms, that give you finite size effects. Okay, so this sort of model.
Sorry, Luke, we're gonna have to wrap up pretty soon.
Yeah, I will finish here in just very quickly.
Okay, thanks.
Okay. So we've implemented this for generic Skirm models in this SRO EOS framework, and included a transition to nuclear statistical equilibrium at low density. So there are a large number of equations of state that we have available for this. But one issue with this is that surface terms can break the thermodynamic stability that you had in the Gibbs construction. So we once again need to account for a possible phase separation through maybe a Maxwell construction, and that's not done. So I think hopefully in the next few months, we'll get that working, and then maybe these will be a little bit more useful for simulations of mergers, because I've heard that there are a couple cases where some of these break. Okay, and you can look at, okay, what's the phase diagram for these, and it ends up looking pretty similar to what you would get for the Gibbs EOS. Okay, I just very briefly wanted to say, okay, well, we've done something like where we varied these various properties of nuclear matter near saturation density and looked at its impact so we varied these properties of saturation density nuclear matter systematically and looked at its impact on core collapse supernovae and the core collapse supernova explosion mechanism. And so we've produced maybe 100 equations state varying these. And I think it would be nice to think about trying to do something like that, but for neutron star mergers. So I won't go through the details of this since I've run out of time, but I'll just put up my conclusions and say thank you for your attention.
All right, thank you very much. I hear a lot of clapping in the imaginary background. Again, I'm switching over to the participants to see anyone raising their hand. And first comment, first question from, I'm so sorry if that's spelled correctly, I cannot pronounce it. Zavolod. Just unmute yourself and ask your question. Thanks.
Thank you very much. Thank you for the very interesting talk. I have a rather naive question about the nucleosynthesis. So you mentioned that nucleosynthesis mostly dependent on electron fraction, and as far as I know, mostly it was computed for dynamic ejecta, which is well, pieces of fluid moving on geodesics, statistical trajectories. But what if you have an outflow, which is like continuous outflow, very hot? Would you expect that the nucleosynthesis there would change and would depend on other properties as well?
Yeah, so I'm not quite sure how hot you're thinking, but certainly the dominant parameters that go into determining nucleosynthesis is, okay, what's the electron fraction around a temperature of 3 or 4 gigakelvin. So when you fall out of NSE and you start neutron capture, what's the entropy of that material at that time? And also what's the dynamical timescale of the material at that time? So those are generally the 3 parameters that have the most impact on, you know, the sort of, you can grossly characterize most nucleosynthesis by those 3 parameters. And as long as the entropy is low, and so by low, I mean maybe less than 30 kb per baryon, there's a limited impact of the entropy on what nucleosynthesis you get. So, and that's generally sort of in the range you would get for dynamical ejecta or ejecta from the disk or something like that. But certainly if the entropy, so if you had, you know, some material that was strongly shock heated or neutrino driven or, you know, whatever, so somehow heated so that the entropy got up to, you know, maybe 100 kb per baryon, then the entropy can also play a large role, because as you go to higher entropy, that just means you're going to lower density at the time that nucleosynthesis occurs. And if you've gone to that lower density, you're going to be much less efficient at maybe taking alpha particles and forming heavier nuclei from them. So forming carbon-12, because you have to overcome this, triple alpha, so you have a strong density dependence. So the higher the density is, the less efficiently you form heavy nuclei, and then the larger you make your neutron to seed ratio, and the more likely you are to make heavy nuclei. So I don't know, that's a long-winded answer.
Thank you.
Thanks a lot, Luke. We are now going to move on to the next talk.